Okay, so thank you for the invitation. Do come in. And I don't know, I would guess that some of you have heard of neutrinos, probably some of you haven't. Probably not very many of you know very much about neutrinos, because in recent years the Higgs boson has grabbed most of the limelight when it comes to discoveries in particle physics. But I'm going to try and persuade you over the next 3/4 of an hour or so that neutrinos are just as interesting as the Higgs boson, even if they haven't got quite the sex appeal at the moment. So I'm going to try to survey the whole field of neutrino physics, which is a big deal in 3/4 of an hour. So what you're going to get is the sort of lightning tour, and I hope that this will interest some of you enough that you will find out about it more later. I can assure you that there's a huge amount on neutrinos on the web. My own experiment, T2K, has a public web page, and I know there's a lot about neutrinos on that page because I wrote most of it. So I'm going to talk about how the neutrino was discovered, how we detect neutrinos, why you need a tank of water 40 meters across by 40 meters deep in order to do this. I'm going to talk a little bit about the solar neutrino deficit, which you may have heard of, neutrinos from supernovae, and I'm going to end up by trying to explain why it is that neutrinos might just prove to be the key to life, the universe, and everything. So, discovering neutrinos. Why is that a challenge? Well, the neutrino is a very elusive particle. Neutrinos have no electric charge, they have almost no mass, and they have extremely weak interactions with everything else. If you took a typical solar neutrino and you wanted to stop that particular neutrino, you'd need a detector consisting of about a light year of lead. A detector consisting of a light year of lead is not in fact terribly practical, and I don't think the STFC would give you the money to build one. So essentially they go through life ignoring everything. They can happily go right through the Earth without even noticing. So why would anybody have suspected their existence in the first place? If something doesn't interact, if it's completely invisible, why would you think it was there? You don't go around assuming that invisible, undetectable objects are haunting your every step. And the answer is, in fact, radioactive decay. In the early years of this century, well, last century, the 1900s, radioactive decay was a big deal. It had been discovered in the dying years of the 19th century. It was cutting-edge research science. And one form of radioactive decay is beta decay. And in beta decay, as I was saying, if you have something like the carbon-14 decay that's used in archaeological dating, carbon-14, as far as you can see, spits out an electron and converts itself to nitrogen-14. So, if you look at that decay, and you apply the most famous equation in physics, E equals mc squared, then what you see is that the energy of this electron should be given by the difference between the mass of the parent particle and the mass of the daughter particle. So what you should see is that our electron should come out with a very well-defined energy which is equal to the difference in those two masses. So you measure the energies of the electrons, and that's what you get. That's a contemporary drawing from 1927. Here's your electron energy spectrum. You will notice that it's not a spike at E equals mc squared. In fact, if it were, then you get a spike right at the end here. So all the electrons have less energy than you thought they were going to have, and some of them have an awful lot less energy than you thought they were going to have. So what's going on? And this was a great puzzle in 1930, and this chap here, Wolfgang Pauli, one of the greats of the early days of quantum mechanics, wrote a famous letter to a conference in which he proposed that the reason for this was that this decay was incomplete, and that in fact what the decay actually looked like was this, and that this particle was electrically neutral, and so in the detectors of the day, which were only sensitive to charged particles, you would not see this particle. He had he had his sense of priorities right. He wrote this suggestion in a letter and had one of his postdocs deliver it to the conference, and he explained in the letter that he couldn't possibly come to the conference himself because he'd been invited to a university ball. So, no, I won't present my groundbreaking proposition to a conference, I'll go to the party. Now, Pauli wanted to call this particle the neutron because it would be neutral, but in 1932 Chadwick discovered what we now call the neutron, and this was clearly not Pauli's particle, it was much too heavy. So Enrico Fermi, another great of early 20th century quantum mechanics, when he developed the first theory of the weak nuclear force, he incorporated the neutrino into his theory. And he was the one who gave it its name. Instead of Pauli's neutron, being Italian, he thought, well, it's lighter than the neutron, so instead of calling it neutron, neutral thing, I'll call it neutrino, little neutral thing. And that's the name it has borne ever since. But although Pauli's theory assumed that neutrinos existed, nobody had ever seen one, because they are so weakly interacting. And in fact, Pauli, as a good scientist, was very worried that he had postulated a particle whose existence nobody was ever going to be able to prove. And the whole idea of science is that you ought to be able to test your hypotheses, so having a hypothesis that nobody can test is not very good science. So Pauli was actually quite concerned about this. And the problem, as I said, is that the interactions are so weak that neutrinos are very hard to see. Now, the key point about this is that this is statistical. Although, if you want a particular neutrino to interact, on average, you need a light year of lead. If you have a very, very intense source, some of them will interact straight away. It's a bit like buying lottery tickets. Generally speaking, most people might buy a lottery ticket every week for their entire lives and never win more than a few £100, never win the big £1 million jackpot. But I'm sure that there are some people who have bought one ticket and it's been the critical one. And the key point is that if enough people do things, then even rare events happen frequently. And so if you have a sufficiently intense source of neutrinos, then the chances of some of those extremely numerous neutrinos interacting in your detector becomes worth doing. So in the 1950s, Fred Reiners and Clyde Cowan decided to detect the neutrino. Reiners had worked for the Manhattan Project in Los Alamos, and he decided he was entitled to some time off to do pure research instead of designing better bombs, and his boss said yes. And Fred sat in his office and thought, what can I do in Los Alamos that's pure research? What do bombs do? Bombs make lots and lots and lots of neutrinos. I can detect the neutrino with a bomb! So, of course, in those days, nuclear testing was all the rage, so acquiring a bomb was not a problem. He said to his boss, can I have a bomb? And his boss said, yes. So he could have a bomb. The problem is that the natural thing for a bomb to do, if you have bomb, delicate piece of scientific equipment, likelihood of delicate piece of scientific equipment being smashed into small pieces, rather high. So you need your experiment to survive long enough to register the presence of neutrinos. So they had a plan. They were going to dig a shaft, evacuate the shaft, so it was a vacuum, and backfill half the shaft and hang their neutrino detector from an explosive bolt. And they had, the idea was that the signal that triggered the bomb would also release the explosive bolt, so that when the shock wave from the bomb hit, the detector would be in free fall, isolated from its surroundings, and would therefore not be blown to bits. Of course, the trouble with free fall is it works fine until you hit the ground, and so you will notice that the bottom of this shaft is neatly labelled feathers and foam rubber, in order to try to ensure that the detector survives the bomb blast in a vaguely recognisable condition. So his idea was that the neutrinos, they're actually anti-neutrinos from fission bombs, would interact with a proton, convert into an anti-electron, a positron, and to conserve charge, you convert the proton into a neutron. And you will be able to detect the track left by the positron in his detector. Now, one of the issues with any of these reactions like this is that you have background from cosmic radiation. So he had to work out how to get rid of the background from cosmic radiation, and then they realised that after a few microseconds the neutron is actually captured by a nucleus, and that produces a burst of gamma rays. So what you see is actually two signals. First the positron and then the neutron. And so at this point he realised that this actually suppresses the background from cosmic rays quite a lot. In fact, it suppresses it by orders of magnitude. And that means you don't need quite so many neutrinos to see your signal above the background. So, you don't need a bomb. You can use the next most intense source of neutrinos, a nuclear reactor. It's the same reactions as take place in a bomb, just taking place slightly more slowly. So you don't get so many neutrinos per second, but you still get a lot, and you can still detect them in the same way. He apparently sent a note to Fermi saying that we've had a new idea, we're not going to use a bomb, we're going to use a reactor. And Fermi apparently wrote back saying, this is a much better plan, you will be able to repeat the experiment. So I think Fermi's view was that the chances of the detector surviving the bomb, despite the feathers and foam rubber, were not very high. So they built a detector. By the standards of the time, it was enormous. It was about the size of this desk. And this was in the days when detectors were more like the size of this coffee cup. In fact, one of the things they apparently did with it, it was about 1 metre cubed. It was big enough to get one of their graduate students inside it. And they measured the ambient radioactivity of a human being. And they said this had never been done before, because with all previous detectors, in order to do this measurement, you had first to reduce the sample to ash. And not surprisingly, they'd been kind of short of volunteers. So they built this detector, exactly the same technique, and this is a sketch of what they were doing. Their target material was water, and in the water, because hydrogen happens to be a good target for this, and in the water they had cadmium chloride, because cadmium is an extremely good absorber of neutrons. It's got a very, very high cross-section for neutron interactions. So your neutrino interacts, produces a positron, the positron finds an electron and annihilates into 2 gamma rays, which you detect. The neutron wanders around for a bit, gets captured on the cadmium, and emits another burst of gamma rays, which you detect. And this is what the detector looked like in the real world, and they ran this detector and successfully obtained signals from neutrinos. So they were able to demonstrate that neutrinos were not a figment of Pauli's imagination, but in fact had a real existence. And this had taken 25 years from Pauli first predicting the neutrino to Reines and Cowan discovering it. Happily, Pauli was still alive at that point. They sent him a telegram announcing their discovery, and he sent them a note back saying, "Everything comes to he who waits." Fred Reines had to wait a heck of a lot longer. He only got his Nobel Prize for this in 1990, which is an appalling condemnation of the Nobel Prize Committee, really. Poor old Clyde Cowan had died by then, and you're not allowed to get the Nobel Prize when you're dead, so he missed out. One of the tricks of the trade in getting Nobel Prizes, as Peter Higgs learned last year, is simply to live long enough. So, the neutrino takes its place in the standard model of particle physics. The standard model of particle physics is the great triumph of the second half of the 20th century in fundamental physics, that we can explain all known particles, both the stable ones and the unstable ones that you can only make in accelerators, with this rather small family of fundamental particles. The quarks, 6 quarks and 6 antiquarks, 3 charged leptons, the electron, the muon and the tau, the muon and the tau being 2 particles with very similar properties to the electron, but much greater masses, and it turns out that each of those has an associated neutrino. And you can tell them apart because if you have a muon neutrino beam and they interact, you get muons out and not electrons or taus. And the forces in this model are carried by other particles, so when you have magnetic forces, that's the exchange of a photon, a particle of light. When you have strong interactions, that's the exchange of a particle which is called the gluon, because it glues quarks together. So these 3 neutrinos all have similar properties. They all have no charge. They all have very nearly no mass. They interact only via the weak force and gravity. They don't feel the strong force that holds protons together in the nucleus, and they don't feel the electromagnetic force, which only talks to charged particles. And as far as we can tell, they are completely stable. So, as I say, you recognise the difference when they interact because they will produce their own respective charged leptons. Now, in the standard model as it was constructed in the 1970s, there were these 3 types of neutrinos were completely distinct. They had antiparticles which were different from the particles, and they had absolutely 0 mass. And this is the one aspect of the standard model which has otherwise stood the test of time that has proved to be absolutely not right. They were wrong. The standard model was wrong about neutrinos being massless. It was wrong about these 3 types of neutrinos being absolutely distinct. And although we don't know this for certain, the odds are quite strong that it was wrong about neutrinos being different from antineutrinos. But all of the... So in the last 20 years or so, neutrinos have forced us to revise the standard model several times, and that hasn't happened with any of the other particles. All the other particles have behaved just the way the theory said they ought to behave. So that's one of the reasons I like neutrinos. So how do we detect neutrinos? In order for a particle to be detected, it has to interact with your detector. If it does not interact with your detector, it hasn't changed anything in your detector, and therefore there is nothing to detect, because a detector detects change. And there are 2 ways in which it can interact. It can either do what Reines and Cowan detected, which is what's called a charged current interaction, where it exchanges a W particle, and these have electric charge, so you convert from a neutral particle here to a charged particle here. So electron neutrino to electron, muon neutrino to muon, and so on. And in that case, what usually happens is that the detector is designed to detect that charged lepton. The other possibility is that they can exchange a Z particle. That is neutral, so the neutrino stays a neutrino, so this you cannot detect. What you detect is the fact that this carries energy and momentum, so you transfer energy and momentum from the incoming neutrino to whatever it hit. And so you may detect what it hit suddenly shooting off in some random direction, or it may hit with sufficient force to break up the thing that it hit, and you detect the products of the breakup. Either way, these are rare interactions, and so you need a big detector. The more detector you've got, the more chances of one of these weak interactions taking place, and this means if it's big, it's got to be cheap, because you can't make a the detector I work on weighs 50,000 tons. I can't have a 50,000 ton silicon microstrip detector because it will bankrupt the entire country, never mind the STSC. It's not doable. So what do we have that's cheap? There are various things we have that's cheap. The first large-scale neutrino detector was this thing here. This thing here is a tank of dry cleaning fluid. It's perchlorethylene, C2Cl4. And the reason it's that is that chlorine is a good target for neutrinos. If a neutrino hits a chlorine nucleus, specifically a nucleus of chlorine-37, which is about 25% of natural chlorine, there is a reasonable chance by neutrino interaction standards, in other words it's tiny but it's measurably tiny, of converting a neutron to a proton and converting the chlorine-37 nucleus into an argon-37 nucleus. And that argon-37 nucleus you can extract from your detector, and it's unstable, it decays with a half-life of about a month, so you measure the beta decay. And this was the first solar neutrino detector. The problem with this is that because what you detect is the decay of an unstable particle that was produced at some undeterminate time earlier, you don't have any directional evidence. You can't tell that these things are really coming from the sun, and you don't have any timing information. You can't tell if they came at a specific time. You only know that they came between last time you emptied out all the argon and this time that you emptied out all the argon. It's used, but the key point is that you don't need a very energetic neutrino to do this, so this is used a lot for solar neutrinos which have very low energy. The method that the detector I work on uses is called Cherenkov radiation. Now, Cherenkov radiation comes from the fact that when we say that nothing can travel faster than the speed of light, that is not a complete statement. What one should say is that nothing can travel faster than the speed of light in a vacuum. Now, if light goes through glass or water, it slows down. That's refractive index. That's why those of you wearing glasses or contact lenses, that's why your glasses or contact lenses work. And that slows down the light by about, in the case of glass or water, to about 3/4 of its speed. More if you've paid extra for high refractive index glasses. The particles are not slowed down. So it is perfectly possible for a particle to travel faster than the speed of light in glass or in water. And if it does so, then you get an effect called Cherenkov radiation, because it basically outruns its own electromagnetic radiation, and what happens is that the wave crests, which are represented by these green lines, add up coherently to produce a coherent conical wavefront. And this is exactly analogous to a sonic boom, and in some cases when you have humid air, you can see this conical shot front. In the case of a sonic boom, here is an aircraft breaking the sound barrier, and here is the cone formed by coherent sound waves. You see this blue light for example, in research reactors, where this is cooling water, the blue lighting here is not some sort of performance art installation designed to make nuclear power look warm and cuddly. It's Cherenkov radiation produced by the beta decays of fission fragments. And because it's a cone, you can measure the axis of the cone and know what direction your particle is travelling in. If I blanked out the image of this aircraft and just left you with the cone, you could still work out which way the aircraft was going. And because it's instantaneous, or at least the speed of light, you also know when your event took place, when your neutrino or your charged lepton passed through. It has to be a charged particle, this, because it has to interact, it has to emit electromagnetic radiation. So you can't detect a neutrino directly through this effect. You detect the charged lepton that it turns into. And the more energy the particle has, the more light it emits. So you get some measurement of the energy as well. So this is these are two examples of neutrino detectors that use this technique. This is the detector that I'm involved with. This is Super Kamiokande. This is in a Downer zinc mine in Japan. This is, as I said, it's a cylinder. It's 40 meters in diameter and 40 meters high. So it's kind of like a dozen Olympic swimming pools stacked on top of one another. And the mass of water is about 50,000 tons. So we believe in providing our neutrinos with lots and lots of opportunities to interact. However, if you want to measure, and this is an event in Super K, here is a muon, and it is a circle, it's just distorted because it hit the top of the cylinder. This is the Cherenkov radiation from the muon, and it stopped and decayed, and here you can just about see another fainter circle, and that's from the electron that was the decay product of the muon. We're very proud of that detector, but in fact, if you want to detect high energy neutrinos from astrophysical sources, it's not big enough. There are limits to how big a hole you can build. The best astrophysical neutrino telescope operating today is IceCube, and they took the view we don't have to build a water tank, nature will do it for us, and they have sunk photomultiplier tubes, sensitive light detectors, 1.5 kilometers down into the Antarctic ice cap. So you're actually using the deep ice in Antarctica as your Cherenkov radiator. They have instrumented about a cubic kilometre of Antarctic ice, which is why they're called IceCube. So you drill your holes, you drill a hole in the ice pack by using a hot water hose. While it's melted, you drop your cable with the electrical power and the photomultiplier tubes down the hole, you let it refreeze, and you do that again lots of times. So these detectors, although they look very different, they both use the same technique. To give you an idea, there's the Eiffel Tower to scale for IceCube. I believe there's an American version of that diagram that has the Statue of Liberty, but so if you thought Super K was big, it's nothing to IceCube, trust me. So that's a quick sketch of how we detect neutrinos. What science can you get from neutrinos? So first, I'd like to talk about neutrinos in the sun. Now, the sun fuses hydrogen to helium. So you take 4 protons and you convert them to a nucleus that has 2 protons and 2 neutrons. So you've got to get rid of 2 units of positive charge, so you emit 2 positrons. There's an accounting rule that says you can't do that, so you have to emit 2 electron-type neutrinos to balance the total number of leptons that you produce. The 2 anti-electrons count -2, the 2 electron neutrinos, count +2, total 0, you're okay. Now, because we know how much light the sun puts out, we can calculate that per square centimetre per second on Earth there are 65 billion neutrinos, 65,000 million. So that's per area the size of a sugar cube, roughly. Doesn't matter what time of day it is, because these low energy neutrinos can go through the Earth without even noticing. Unfortunately, most of these are very low energy, so they're difficult to detect even by neutrino standards. But this was what Ray Davies used his tank of cleaning fluid for, and what Ray Davies found was that he only measured about 1/3 of the number of neutrinos he was expecting. And the predecessor of Super Kamiokande, Kamiokande 2, also detected solar neutrinos, and they detected about half of what they were expecting. This became known as the solar neutrino problem. And it was not initially clear whether it was a problem with the sun or a problem with the neutrinos. In fact, when I was an undergraduate, each camp was blaming the other. The solar physicists were saying, we understand the solar interior, it's you and your neutrinos. And the particle physicists were saying, we understand neutrinos. When we do neutrino experiments in the lab, they all behave perfectly. It's you and your solar model. So it was difficult to resolve this, and for several decades it remained unresolved. And the way to deal with it was to count all the neutrinos, not just the type that are associated with the electron. And this was finally achieved by an experiment called SNO, the Sudbury Neutrino Observatory. And SNO was built in Canada. And the key reason for building it, and it's quite large, it's not as big as Super K, but there's a standard person, just to show you it's quite big. The key reason for building it in Canada is that Canada's nuclear reactor program uses heavy water, deuterium oxide, as a moderator. So they had lots of deuterium oxide, and they were prepared to lend it to SNO. If SNO had leaked, they'd have been in trouble, but it didn't. And the thing about deuterium, a proton and a neutron bound together, is that it's a very weakly bound nucleus. It's almost not stable. It's just barely stable. And so if you hit it with a neutrino, it falls to bits. And it can fall to bits in one of two ways. If you hit it with an electron-type neutrino, you can get the same sort of reaction that Reiners and Cowan saw. You can convert the neutron in deuterium to a proton, and you get out 2 protons and an electron. But if you hit it with any kind of neutrino, you can also break it up into its constituent proton and neutron, and the neutrino stays a neutrino. So this can only work with electron-type neutrinos. This can work with any type of neutrinos. And when they did that, there's one of their events. You see the Cherenkov circle there. What they found was that they did indeed see only a fraction of the number of electron neutrinos they expected, but when they looked at this reaction, the blue one, they found this blue line, and if you compare that with the theoretical expectation, which is somewhere inside this pair of dotted lines, you can see that the total number of neutrinos is fine. It's just that they're not all electron-type neutrinos. So what this does is it's a total vindication for the solar physicists. The model of the sun was right. The model of the neutrino was dead wrong. It is not true that if you make a neutrino as an electron-type neutrino, you always observe it as an electron-type neutrino. There is some probability that it will change its flavour. Now this is a shock. This is very much unlike what all other particles do. The protons in making up the hydrogen in your body don't spontaneously change into neutrons. Very lucky for us that they don't. But it does happen with neutrinos. So that resolved the problem with the sun. Now, many things in astrophysics should emit neutrinos, and we have detected one other thing that emitted neutrinos, and that was an exploding star, a supernova. Massive stars, stars that weigh 8 times as much as the Sun or more, when they get to the end of their lives, they have fused all the elements up to iron. Iron is the most tightly bound element, so fusing iron doesn't gain you any energy. So when they make an iron core and it collapses under gravity, fusion will not stop it. And what happens is that iron core collapses to form a neutron star, which is basically a single atomic nucleus weighing 1.5 times as much as the Sun. And the rest of the star falls onto this very rigid surface, bounces off, and this creates a stellar explosion, a supernova. And when the neutron star forms, protons and electrons combine to form neutrons and emit neutrinos. Also, the interior of this collapse is so hot that you can form neutrinos by interactions like E plus E minus goes to neutrino, antineutrino. And it turns out that even though supernovae are the brightest things in the galaxy, you're only seeing 1% of the energy. 99% of it comes out as neutrinos. So supernovae are neutrino bombs. Furthermore, if it weren't for neutrinos, they wouldn't explode. Neutrinos drive the shock wave that drives the explosion. We have seen so far precisely one supernova in neutrinos because there's only been one that was close enough to produce a big enough flux to be detected given weak neutrino interactions. This was the famous supernova 1987A in the Large Magellanic Cloud. So this is the Large Magellanic Cloud before February 1987. This is the Large Magellanic Cloud in February 1987. This thing here is a star called Sanduliac minus 69202. It was a blue supergiant, it's not there anymore. And it got out up to magnitude 3. It was the first naked eye supernova since 1604. It's one of the very rare cases where the guy who discovered it, Ian Shelton, was able to check whether he got it right by going outside the dome and having a look. This is not the way you usually check astronomical discoveries. Three experiments, well 2 really, Kamiokande in yellow and IMB in red detected 20 neutrinos between them from this supernova. They arrived about 3 hours before the light because they can get through the dense material of the supernova before the photons can. The blue ones were detected by a Russian experiment called Baksan. On its own, that would not have been distinguishable from noise, but it was at the same time, so these probably are also from the supernova. This was more fortunate than it looks. At that time, Kamiokande had a technique where every few hours they routinely turned their detector off for 3 minutes to calibrate it. If the burst had been 3 minutes earlier, they'd have missed it. In fact, a guy who was on this experiment told me that if it hadn't been the Japanese equivalent of a bank holiday, when the schedules are slightly different, that calibration would have taken place there and they would have missed it. This was a nasty shock, and immediately afterwards they changed their calibration strategy so that they didn't turn the whole detector off, they only turned one section of it off at a time so that would never happen again. Even IMB were lucky because a quarter of their PMTs had tripped off due to a high voltage fault, and so normally that data would have been thrown away as not useful, but fortunately they were able to recover it. So we were lucky to get that burst, but we did get it. It's only a couple of dozen neutrinos. It tells you that the model is basically right, but it's hard to get more information from it. This does not, of course, stop theorists trying, and I should imagine that each of those neutrinos has about 10 research papers it can call its own. So finally, having talked about neutrinos and the sun and neutrinos and supernovae, I'd like to look at the big picture and talk about neutrinos and the universe. Now, matter in the universe, the key thing about matter in the universe is that it's matter in the universe. It's not antimatter in the universe, and it's not a 50-50 mix of matter and antimatter in the universe. Why not? matter at the LHC, we always make equal quantities of matter and antimatter. You always, if you use E equals mc squared to make a heavy particle that's not existed since the dawn of time, you always make it and its antiparticle in a pair. And this is surprising. This is not surprising. They're mirrors of each other. Their masses are the same. Their interactions are very, very nearly the same. Why are they not produced? They should be produced in the early universe in equal quantities. So why are they not present in equal quantities now? They certainly are not, because matter and antimatter, when they come together, annihilate. And if there were antimatter stars out there, we would see the effects, because stars don't just produce light, they also produce stellar winds, which are fluxes of charged particles. We would see the annihilation radiation from when the solar winds from stars met the solar winds from anti-stars. And this does not happen. Now, back in the 1970s, the Soviet theoretical physicist Andrei Sakharov, nowadays better known for his political activism, but he was a very distinguished theoretical physicist as well, put forward 3 conditions under which such an asymmetry between matter and antimatter could be generated. The first of these is that there must be interactions that violate baryon number. In other words, there must be interactions in which the total number of protons minus the total number of antiprotons before the reaction is different from the total number after the interaction, obviously. Otherwise, if the total number of net number of baryons before was 0, you'd never get anything other than 0. It turns out that the Standard Model at very, very high energies, it turns out that the Standard Model does predict such processes, but they're processes that are quantum mechanical tunneling type processes that can only happen at extraordinarily high energies, very early in the history of the universe. You also need a lack of thermodynamic equilibrium. Thermal equilibrium is a stable state, and in thermal equilibrium, the rate of the forward reaction is equal to the rate of the backward reaction. And obviously that won't do, because if you have thermal equilibrium, if you have some hypothetical interaction that generates baryon numbers, it's going in the same direction, it's going at the same rate in the opposite direction, where it destroys baryon number. And the final condition is something called CP violation, which is 50 years old this year. What, you ask, is CP violation when it's at home? It sounds vaguely dubious. It's a kind of mirror reflection. To a particle physicist or a quantum mechanic, C is an operator which takes all particles and exchanges them with their antiparticles, and it's called charge conjugation. And P is mirror reflection. P is called parity, and it changes all space coordinates to minus themselves. So x, y, z becomes minus x minus y minus z. And CPs do both at once. And nature behaves something like this Escher etching. If I take this etching and I apply C, so if I call particles white and antiparticles black, and I exchange white for black, I get a picture which is different from the original. I've got white rivers on this side, black birds on this side, whereas here we have black birds and a white river on this side. Also, if I take this picture and apply P, so I flip it round, again I get a picture which is different from the original. Very noticeably different from the original. But if I do both of these things, then I get a picture which is very similar to the original. So, although C and P do not conserve this etching, C and P together does. Almost. Now, you'll notice that it's actually a very good analogy, because you'll notice that this and this are not identical. There is a little boat in the river on this picture, and in this picture it has moved to be in that river. And the same is true in nature for CP violation. CP is almost conserved, strong interactions look right, electromagnetic interactions look right, weak interactions almost look right, but there are a few interactions involving certain classes of particles where there are small differences between the original interaction and the CP reversed interaction. But if you work out how much asymmetry between matter and antimatter that would cause, it's not enough. You and I would not exist if you could only use the CP violation found in the interactions of quarks. The other place where this might happen is the neutrino sector, and that is a consequence of this fact that neutrinos are not immutable, that they can change their type. You need all three types of neutrinos to be involved. Two we know about, solar neutrinos I told you about, and the neutrinos that are produced in cosmic ray interactions, which are muon-type neutrinos, are also known to transform into tau-type neutrinos. If you look at the rate of muon neutrinos coming down, it's higher than the rate of neutrinos coming up. And that's not because they've interacted, because they don't, it's too low in energy. It's because they've transformed in the 13,000 kilometres that they travel to come up. Some of them have transformed from muon type into tau type neutrinos. And our detectors are not sensitive to tau type, so we miss those ones. And that's why that happens. And these are experimental results that basically tell you the two things that determine this. One is an angle and one is a difference in squared masses. And those are experimental results that demonstrate that both of those exist. So, the experiment that I work on was chasing the third of these angles, and we make our neutrinos on the east coast of Japan, and we shoot them, and then we make them as muon neutrinos. We shoot them 300 kilometres across Japan to super K, and we attempt to detect, measure what fraction of them have turned into electron neutrinos.